In this chapter, we discuss several ways materials are used to manipulate light for many applications. Often, the polarization of light is key to new technologies, such as this liquid crystal display. This also gives us a good reason to discuss the anisotropic properties of materials in more detail. Recall that light is just a narrow band of frequencies in the electromagnetic spectrum. Thus, the methods we use to describe optical materials are also applicable to materials that help us collect, channel, and analyze radio and microwave devices for wireless communication, as well as ultraviolet, X-ray, and gamma ray applications. Light is an electromagnetic wave, means it is a wave of electric and magnetic field that travels at the speed of light. The electric field interaction of light with matter is related to the dielectric response. The magnetic field is relatively weak. Recall that some properties of light should be treated quantum mechanically, like the interaction with an electron, where a quantum of electromagnetic wave is called a photon. Notice that light has a polarization perpendicular to the direction of propagation. Here, E, the electric field, is along X, with the light traveling along Z. But light traveling in the same direction could also have a polarization along Y. This leads to different responses when either the situation or material involved is not isotropic. For example, even light reflecting off glass interacts differently depending on whether the electric field is parallel or perpendicular to the interface normal. The reflection angle is the same for each polarization. Angle of incidence equals angle of reflection, but the intensity, how much the light is reflected or transmitted, can be different. In this photograph, the light from outside reflecting on the vertical picture glass is so glaring bright you can only see the reflection and not the picture. But when a horizontally oriented polarized filter is used, the reflection is removed and you can see the light coming from the picture on the wall. The photograph is taken close to the special angle known as Brewster's angle, where the reflected light is fully polarized for this picture, but not the other one. Many light sources, such as sunlight, are unpolarized, meaning a uniform distribution of all polarization directions. Polarizing film can be made from a stretched polymer that has very anisotropic optical properties because the polymer chains are aligned by the stretching. In an absorbing polarizer, the film absorbs the light with electric field aligned in one direction only, while transmitting the light with electric field in the perpendicular direction. The polymers are impregnated with long dye molecules or iodine to absorb light polarized along the elongated direction. Today, many polarizing films are reflecting polarizers. They are multi-layer copolymers that have a matching refractive index for transmitting one polarization state and a mismatched refractive index in the other direction to reflect the other polarization state. A reflective polarizer minimizes the amount of light absorbed and therefore more efficient than an absorbing polarizer. From Maxwell's equations, the speed of light in a medium is 1 over the square root of the electric permittivity and magnetic permeability, where the values for free space give the speed of light in a vacuum. All optical materials are non-magnetic, so relative permeability is approximated to be 1. The index of refraction is a measure of how much slower the speed of light is in a medium compared to a vacuum. Thus, the index of refraction is actually the same material property as the dielectric constant, or relative permittivity, with n equals the square root of the relative permittivity. Applications of optical materials often make use of the anisotropic properties of materials, which means different properties in different directions. Recall that electrical conductivity describes the electric current flux produced in a material by an electric field. Since both flux and electric field are vectors, conductivity is actually a second-rank tensor. Similarly, thermal conductivity and here electric permittivity or dielectric constant are also second-rank tensors, which means optical index of refraction is also a tensor. Symmetry requires these tensors to be diagonalizable along three principal axes. This means these properties in any material can be described like an ellipse. For example, you simply need to know the direction, or vector, of the electric field of the light interacting with your material. You then find the components of that vector in each of the three principal directions, and get the property, such as index of refraction, for each direction. In cubic materials, all three principal directions have the same value, so the property is isotropic and can be treated as a scalar. Also, liquids, glasses, and randomly oriented polycrystalline materials behave isotropically. A material with one unique direction, but the two other directions have the same property, are called uniaxial. Tetragonal and hexagonal crystals, as well as films with random orientation in the plane, are uniaxial. In other crystal systems, no matter how low symmetry, the properties can still be described with an ellipse, although only the orthorhombic crystal will have the principal directions match the crystal axes. Here, hexagonal calcite is exhibiting birefringence, where two images are seen through the crystal, an upper image and a lower image of the same lines. Each polarization travels through the crystal with a different index of refraction and a different path. Viewed with polarizing film, it is possible to see only one image, the light from each image being either vertically or horizontally polarized. An anisotropic material can also change polarized light from one polarization state to another. Here we have an anisotropic material with one index of refraction vertical, the green direction, and a different index of refraction in the horizontal direction, blue. If the incident light has a diagonal polarization, red, we can follow what happens to the light by vector projecting the polarization onto the crystal's optical axes, the green and blue waves. The different indices of refraction will make one wave travel faster than the other, leading to an offset in the phase of the waves. Eventually, one wave will fall a half a wavelength behind the other. If the light exits the crystal at this point, the light will have had its polarization flipped perpendicular from where it started. Notice that halfway through this plate, the light has both blue and green polarizations that don't go to zero at the same time. This is known as circularly polarized light. Some rod-like molecules have a stepwise transition as they go from a fully ordered crystalline state to a fully disordered isotropic liquid. For example, they might lose some orientational order or disorder in one direction but remain ordered in another direction. This gives them properties between liquids and crystals that we call liquid crystals. Having some anisotropic crystalline properties, they can change the polarization of light. Viewed in a polarized light microscope, they show beautiful microstructure not commonly observed in crystalline solids. Some chiral molecules can make liquid crystals with a twist that also affects the light. In a transmission-based liquid crystal display, a liquid crystal rotates the polarization by half a wave so that the light transmits under crossed polarizing filters. This leads to a bright pixel in the display. When a small electric field is applied to the liquid crystal, the molecular orientation is changed so that the optical transmission is isotropic, and the crossed polarizers filter the light, making a dark pixel. Because materials interact in different ways with each color of polarized light, they will show distinctive and colorful patterns when viewed with polarized light. These crystals are imaged using a polarized light microscope. Geologists have been using such optical microscopes for a long time to identify minerals based on the crystal morphology and their interaction with polarized light. Reflecting light can also be used, such as this observation of an aluminum welding seam where the grain structure is clearly visible. In this biological specimen, the muscle fibers and other tiny organ structures are clearly visible using polarized light.